when you hear the word alcohol, you likely think of alcoholic beverages. Alcoholic beverages contain ethanol, which is the key component of those beverages that creates their alcoholic properties. Now, ethanol is a small organic molecule shown here that is an alcohol. Now, alcohols are defined based on this oxygen and hydrogen that are bonded to our carbon structure. So we have our two carbons over here on the left of our ethanol, and we have our oxygen and hydrogen bonded at one end of our molecule. This is what we call the alcohol functional group. And there are actually thousands of different molecules that have this alcohol functional group, including many common and important molecules in our bodies, such as sugars, or many of the different lipids and proteins that we have as well. Now, all of our different alcohols, as I said, will contain this oxygen and hydrogen. We can represent any alcohol using the basic formula with R bonded to our oxygen and hydrogen. This R is just representing any kind of carbon-based structure. Right? So in this case of our ethanol, it's our two carbons, but of course it could be hundreds of carbons or just a few carbons depending on the size of the particular alcohol that we're looking at. Now, this particular alcohol group, this functional group, is going to have unique properties and reactivity associated with the properties of that oxygen and that hydrogen that are attached. In the case of our ethanol here, we can actually react it in what we call an oxidation reaction, and we can create acetaldehyde. So we lose our hydrogen and gain a double bond to our oxygen. And when this compound actually is toxic, and so when this process occurs in our body, that ethanol that you might consume gets converted into this toxic product, and that leads to a lot of the negative consequences of hangover and the eventual liver damage that makes alcohol dangerous. Now, the reactivity of alcohols is just one of the things that we need to consider in order to understand our alcohol functional group. We also want to look at the naming of our alcohols, right? So we use our systematic naming system in order to determine what our structure looks like just from the name, or to determine what kind of name we have just by looking at the structure. We also want to look at the physical properties of our functional group. So we want to look at what the melting point or boiling point is, whether it's going to mix and be soluble with water, and then of course that reactivity as well. In this case we have that oxidation reaction that I just mentioned that leads to those dangerous effects of alcohol. So we're going to take a look at each of these three things for our alcohols as well as for our alkyl halides. Now, alkyl halides are a functional group that is somewhat similar to alcohols, but will also have some key differences that we'll discuss. So an alkyl halide contains, again, carbons, but then it has an electronegative atom attached to those carbons. In this case, I'm using X representing any of my halogens. So remember, your halogens are in group 7A at the right-hand side of the periodic table. This can be fluorine, chlorine, bromine, or iodine as our common halogens. So X could be any of those. And again, our carbon structure as well can vary here for our alkyl halides. So we can represent this as R, X, where R represents any kind of carbon structure, and X represents one of our four common halogens. The first thing that we're going to look at is how we can name these functional groups. Now, previously when we looked at naming, we talked about how we can use prefixes to tell us how many carbons we have in a given structure. So in our two carbon structure here, we used a specific prefix for two carbons, which was the F prefix. So we have F, and then normally we would end this with a and E ending. So when we have just two carbons, we call it ethane. Now in this case, we don't have just two carbons, right? We have two carbons, but then we also have our alcohol functional group. So we need to add something new onto our name in order to tell us that we have a functional group here instead of just 2 carbons. So what we're going to do first is we're going to add a functional group name in the form of a suffix to tell us what functional group we have. So we're going to use, instead of saying ethane, we're going to end it with OL to indicate that we have an alcohol. So this becomes ethanol when we add that OL from our alcohol. So we're simply replacing that NE ending with our NOL ending to indicate the presence of this alcohol functional group. Now, the second key thing that we need is we need something that can tell us where our functional group is. In the case of ethane, it doesn't really matter because we just have 2 identical carbons, but let's say we have a larger alcohol. So if I draw out my 4 carbons and my alcohol, so since I have 4 carbons here, 1, 2, 3, 4, I would call this butanol. You should remember but is our prefix that means 4. Again, I'm just using that OL ending to indicate the presence of my alcohol. But butanol is somewhat non-specific, right? I'm just saying that there's 4 carbons and there's an alcohol. Well, I could draw this again, and I could put now, butanol is somewhat non-specific, right? It just indicates that we have 4 carbons and that OH of my alcohol. So what if I take my 4 carbons and I put them together, and then I decide to put my alcohol here instead? Now I have a different molecule, right? It looks different, has a different shape. My OH of my alcohol is in a different spot. So I need a new name for this new structure. So the second thing we need is a number to indicate the position of our functional group. So, in the case of my butanol here, my OH is attached to the first carbon, so I can put 1 butanol here. Now you might say, why did I determine this was the first carbon instead of the 4th carbon, right? If I count from the left, that looks like the 4th carbon. Well, remember our key rule for numbering our structures and naming our structures is that we always want to use the numbering system that gives our first branch or our functional group the lowest number possible. So we're always going to want to name it from, or number it from the right, in this case, because that will give us the lower number of 1 for our, the position of our alcohol functional group. Up here I'm going to do the same thing. 1, 2, 3, 4. In this case I'm numbering it from the left in order to give the lowest number to my alcohol functional group of 2. So my structure at the top would be 2-butanol, and my structure on the bottom here is 1-butanol. Now let's look at the case of our alkyl halides. So our alkyl halides are going to look a little bit different because instead of using a suffix like we did with our alcohol, we're actually going to use another prefix. So for our alkyl halides, we're going to have our prefix, and it's going to be based off of the name of our halogen. So our general prefix is going to look something like this. We'll have our halogen name ending with O in front of the name of our molecule. So again, remember, we have 2 carbons that use our F prefix. And so we'd start out with ethane if we don't have our halogen here. And then we're going to add the name of our halogen in front of it. So let's say we have fluorine. So we take the front part of our fluorine name and we end it with an O. And this is going to be fluoroethane. Or if we have chlorine, then it would be chloroethane. Right? Chlorine, you're just taking the first half of the name, ending with O to get our prefix for that alkyl halide. Following the same basic rules, our bromine would give us bromoethane, and our iodine would give us iodoethane. So again, we're always just taking the first part of the name of our halogen and then ending it with O and putting it in front of the name of our carbon molecule to get the overall name of our alkyl halide. So we have 4 different prefixes: fluoro, chloro, bromo, and iodo. Now again, we also have to add a number here to indicate where our functional group is, just as we had to do with our alcohol. So again, we might have an alkyl halide with multiple carbons. Here we have 5 carbons, so we use our prefix for 5, which is pent. So this would be pentane. And now, let's say I have a bromine over here on the right. So I need to use a number to indicate where my bromine is. I know that it's going to be called bromopentane because that's my prefix for bromine. But I just have to add a number there to tell me where it's at. If I number from the left, I get 4. If I number from the right, I get 2. I want to use the smallest possible number to indicate where my bromine is. So this becomes 2-bromopentane. If I have both functional groups combined in the same molecule, so let's say I have an alcohol functional group on here as well, I just need to add the suffix for my alcohol in addition to the prefix for my alkyl halide. So I'd replace my ending E here with my OL to tell me where that alcohol is, or to tell me that I have that alcohol. Now I just need another number here to tell me where that alcohol is. So I already used the numbering system before of 2 for my bromine, so that would give me 4 for my alcohol. However, we're going to introduce a new rule here. So whenever we have multiple functional groups, our alcohol is going to take priority over our alkyl halides. And what we mean by that is we always want to give our alcohol the smallest number, and then our alkyl halide or any other branches that we have on our molecule. So we actually would switch here to use our pink numbering system, and we would have a 2 for our alcohol. I'm going to put that number in front of my name here that indicates my alcohol, and then I'll have a 4 for my bromine. So it becomes 4-bromo-2-pentanol. And I should mention here that you can also put the 2 directly in front of the suffix that indicates what kind of functional group you have. So I could also write this out as 4-bromo, 4-bromopentan, 2-ol. Both of these are perfectly appropriate ways of writing out the name. So using these key rules, we can name our alcohol molecules and our alkyl halide-based molecules. We can even name molecules that have both of our groups combined. Right? So this molecule is both an alcohol and an alkyl halide. Right? It has that bromine and my OH, my hydroxy group, I call it, because it has a hydrogen and an oxygen. And I can use my rules to name it, and of course I could use my name to determine what my structure looks like. Next, let's take a look at the properties of our new functional groups here. Now, as I already mentioned, both of our functional groups here use electronegative atoms. So electronegative atoms, again, are the atoms on the right side of our periodic table and also the top side of our periodic table. And what those electronegative atoms do is they pull electron density towards themselves. So I have my oxygen that's highly electronegative. It's going to be pulling electron density away from my hydrogen and my carbon in both of these bonds, creating my bond dipoles. And my halogens also tend to be electronegative and pull electron density away from my carbon and towards those halogens. Of course, my halogens do vary somewhat in electronegativity. Fluorine is the most electronegative since it's at the top of the periodic table, and we decrease our electronegativity as we move down the periodic table. So chlorine, bromine, and finally iodine each have slightly less electronegativity. But they all tend to want to pull electron density towards them. As we discussed earlier, this has a significant effect on our reactivity and our properties. So as we pull electron density towards ourselves, this creates our dipoles. We have our partial positive charges that develop and our partial negative charges. As those electrons are redistributed, and that allows for dipole-dipole interactions. So we can have these interactions between our partial positive and partial negative charges that can then hold our molecules together and lead to higher boiling points and melting points. Right? Our molecules are more stuck together by these interactions, and they're less likely to pull apart into those more expanded states like the liquid and the gas state. So both of these functional groups tend to have higher melting points and boiling points compared to alkanes. Remember, alkanes only had the weak London dispersion or van der Waals interactions holding those alkanes together. Now, of course, that is dependent upon size, since as we increase the size, we're always increasing the strength of the interaction between those molecules. So a small alcohol or alkyl halide is not necessarily going to have a higher boiling point than a very large alkane. But if you're looking at similarly sized compounds, they will tend to have higher melting points and boiling points. Now, we do have a key difference here, though, between our alcohol and our alkyl halide. And that is our hydrogen over here on the right side of our alcohol. Now, remember, when we have hydrogens attached to highly electronegative atoms like our oxygen, our hydrogen, since it's not very electronegative, will experience a significant dipole towards our oxygen. And that leads to the possibility of hydrogen bonds forming, where our strong bond dipole from our oxygen and hydrogen can then interact with the dipole of nearby electronegative atoms like our oxygen, and we can create this hydrogen bond. So my hydrogen bond I'm representing by my dashed lines between my hydrogen that becomes electron poor and my oxygen that becomes electron rich. So we have hydrogen bonding over here for my alcohol, but of course my alkyl halide, it doesn't have that hydrogen, and so it doesn't have hydrogen bonding. So our alcohols will actually tend to have higher boiling points and melting points compared to our alkyl halides. Even though alkyl halides have those dipole-dipole interactions, they're not as strong as the hydrogen bonding that we can have with our alcohols. So in terms of our melting point and boiling point, we can say that alcohols will have the highest boiling points with their hydrogen bonding. Then we'll have our alkyl halides. And then we would have alkanes. Again, of course, this is assuming that all of these compounds have similar sizes. As we saw before with our alkanes, these intermolecular interactions will also affect our solubility. So in terms of solubility, the more hydrogen bonding we have, the more likely we are to be soluble with water, since water also uses hydrogen bonds. So in terms of solubility, our alcohols will be relatively soluble, right? They can form hydrogen bonds with water, and so most of those alcoholic beverages are actually mixtures of water and ethanol. Our ethanol is able to hydrogen bond with other ethanol molecules as well as with water molecules, and they're all happy together in those beverages. Alkyl halides, they can't hydrogen bond with our water, and so they don't mix as well with water. They're not as soluble. So in terms of our water solubility, we get the same basic trend. Alcohols tend to be relatively soluble, and those are much more soluble compared to alkyl halides. Alkyl halides can be a little bit soluble because they can use those dipole-dipole interactions to interact with water somewhat. And of course, alkanes aren't really soluble at all. Now I should mention that this does depend on size. If you have a very large alcohol, so let's say we have an alcohol where we have a whole bunch of carbons and then our single alcohol functional group. So we have our alcohol functional group right here that can do hydrogen bonding, but the rest of our structure over here really just acts like an alkane, right? It's just carbons and hydrogens. It doesn't have any dipoles associated with it, doesn't have any hydrogen bonding, and so it actually behaves a bit more like an alkane and becomes insoluble in water. So this trend holds true overall, but the size will affect the solubility. One final factor here that we can consider for our alkyl halides, and that is the impact of our different halogens. So remember our halogens, so we start with fluorine at the top of the periodic table, followed by chlorine, bromine, and iodine, moving down the periodic table. Now one of the things you should remember from general chemistry is that as we move down the periodic table, our atoms get progressively bigger. Right? So fluorine is going to be relatively small, and then we go to chlorine, and chlorine has a lot more electrons around it, and those electrons are what create most of the size of our atom overall. So chlorine gets a bit bigger as we add another layer of electrons. Bromine is even bigger than that, and iodine is the biggest of all. So you're going to have a size difference between these atoms, and that's also going to create a difference in their physical properties. A very large atom, like our iodine, so of course this atom is large because we have lots of electrons. They're all kind of floating around in this space, this electron cloud, around our nucleus at the center of our atom. Now, this large cloud of electrons actually creates polarizability. Polarizability is the ability of our electron cloud to kind of get distorted and the distribution of our electrons to change. Remember, with our van der Waals or London dispersion force, that force occurs because we have a random distribution of our electrons creating these sort of small temporary differences in charge or dipoles, and that leads to our interaction. When we have very large clouds of electrons, our molecule becomes very polarizable in the sense that we have a lot of electrons that can move around and create those sort of London dispersion interactions. So larger atoms like our iodine actually tend to have stronger interactions compared to our smaller atoms like our fluorine. So polarizability actually means that for our alkyl halides, our iodine-based alkyl halides will have a higher boiling point than our bromine, which will have a higher boiling point than our chlorine-based alkyl halides, which will have a higher boiling point than our fluorine. So this is the trend of our polarizability, and then we can also say that a higher boiling point results when we have a higher polarizability. Now that we understand a bit about the naming and the properties of our alcohols and alkyl halides, we can start to look at our reactivity. Again, the first thing we should remember is that reactivity is highly dependent on our electronegativity and what our molecule looks like in terms of electron density. Where do we have areas of high electron density, those nucleophiles, and where do we have areas of low electron density, our electrophiles. Now, for our alcohols and alkyl halides, since we have these electronegative groups that are going to create these areas of high electron density, they're actually quite reactive. So we're going to see a lot of different reactions for our alcohols and our alkyl halides, and we're going to look at those in separate lectures. So of course, for our alcohols, you've already seen oxidation, which we'll talk about in more detail later. But one of the key reactions that we're going to see for both alcohols and alkyl halides is what we call nucleophilic substitution. So as the name suggests, we're going to be taking nucleophiles and we're going to be substituting or replacing them between molecules. So our nucleophilic substitution will be taking alkyl halides or alcohols. We're going to be taking our nucleophilic portions, that's the oxygen or the halogen, and we're going to be swapping it out for a new thing that's nucleophilic. So that's the substitution portion of our name. So for example, we can take our alkyl halide, we'll use chlorine, so this would be chloroethane, and we can actually react it with water, and we can, so our water, our oxygen here is going to be acting as the nucleophile, it's going to substitute for or replace our chlorine. So this reaction would produce an alcohol, our ethanol, and a hydrogen halide, in this case HCl. So again, we're just taking the nucleophile and replacing it with another nucleophile in this substitution reaction. And we'll explore the details of this reaction in the next few videos.